To go to be a research institute, right? Which I find little troublesome, but that's the only way we can survive, right? So I personally push for multi-dimensional education, multidisciplinary research, and when I started, when I was taking admission in PhD in mechanical engineering, it was not by choice of the department. It was choice of my. It was by choice of my advisor, right? So in the area where I was going to research, there were some top-notch researchers in that department in that university. So I went blindly that I'll get to work with them, and it started. And then I realized, oh, my PhD is going to be in mechanical engineering. It was, in fact, I realized it when I was 2, 3 years into my program. I was about to graduate. Then I realized my degree that will be given will be in mechanical engineering. And then slowly, since I spent about 10 years, maybe 13 years in Canada, Germany, and US, I realized that people actually love it. Having different type of degrees is something that is loved, and it gives you various facets about how you should think about research, right? Similarly, instead of just being in institutes, just being in educational institute, just being in academia, you should also try to get some exposure of industry. And that is something now I have realized that if I was not part of the industry that I joined after my BTech for a few years, and then the company that I joined after my postdoc, I would have not realized what research is needed at industry level. Continuing to do research sitting in an educational institute just on your desk does not make you a good researcher, because that is the research that you are thinking because it is coming to your mind. You do not know what is needed at the user end, right? So your research is less applicable. You may be happy, but it is less applicable to society. It is not as useful as it should be because the funding agencies are not providing funds for your satisfaction. They are providing funds so that your research can be useful for society, right? So with that, I begin my talk. As I said, that I love materials now, and it is not just material synthesis. It is not just metallurgy. I realized that PhD in mechanical engineering has uh, forced me to think about how materials survive. So you can make them in the lab, you can produce them, but then their survival is very important because they are used in some component. When I say component is not just truck or tank or things like that. Components means any synthetic component that you have created. For example, synthetic skin, or let's say bandage, or anything that you think about, this mic, right? Or just think about material. They are everywhere. You are made of material, and that's how I begin my talk. So this talk will be about machine learning driven accelerated simulations, because I, after doing my BTech in metallurgy, I went into simulations, model development, not just simulation. Simulation is something that you run. Model is developed and you run to simulate what you observe in lab or industry, right? Before that, there is a step called experimental observation. Then you create algorithms so that your observations can reproduce what you see in the lab. And then algorithms cannot run by themselves. You have to program them, right? So you have to do modeling by bringing the mathematical component. So we'll see some examples of how machine learning can be used for accelerating the simulation that we do, and how we can use it for designing new materials which do not exist right now, or may exist maybe with inferior properties, or they are being produced using inferior processes, right? And how we can capture more data, because you will be hearing it again and again that when you do data driven machine learning, and I emphasize, I'm saying data driven machine learning, I'm not saying machine learning. I'll tell you that there are various flavors of machine learning. Here, when I say database development, it is needed for data driven machine learning because these models are data hungry. You need data, right? And trust me that when you start this area of research, the first thing you'll realize is that there is no data. Unless you have your own lab, you own a company, or you're managing data in industry, there is no data. And data is not provided by anyone for free, because data also comes with intellectual property, right? If you are skilled enough, you can extract a lot of information, how that data has been produced, how the material has been developed, where it is going to be used. So there is intellectual property associated with that. So nobody shares data, especially industry, right? So being a researcher, you should know from where the data should come. So I'll also give you some examples of how to automate this database development. And overall, what we are interested as a society and as a nation is that we need to make not just materials but parts, right? Large engineering structures. That is manufacturing. And manufacturing is something, uh, you know, which I often say off the record and also informally, that if you offer a manufacturing job to an Indian graduate like I was, it is the most disliked job, one of the most disliked job. If people tell you that you'll have to work on the shop floor, your hands will be dirty and you'll have to do some measurements and you know making of things by yourself, most of us do not like it. And the truth is that without manufacturing as a nation, we will not survive, right? We are more interested, as now is very well known, in white collar jobs, right? But now there is another domain, so that you can associate this white collar job with actually manufacturing. We can digitize that manufacturing, right? So I'll also take you towards what is digital manufacturing and how whatever is coming in my talk can be helpful for this thing called digital manufacturing or digital twins, right? So I am a faculty member in Department of Mechanical Engineering at IIT Bombay, and this is a lab that I run there. It's called ICME, which is Integrated Computational Materials Engineering and Materials Genome Lab. And I, by accident, found this acronym. Before, imagine, you see the keyword, which is now being used for generating uh, images and videos based on text. I actually invented it before that. It came in 2018. I was not aware of DALI or large language models and all these things. I saw that, I mean, mix of words is giving me imagine. And my idea there was that before we synthesize any material in the lab or in industry, right, we can imagine what is happening, which elements should be mixed together, which process should be used, and we can digitally visualize what is the material there, what is the structure there, right? I'm also affiliated with this center called Center for Machine Intelligence and Data Science at IIT Bombay, which is having about 70 affiliate faculty members from various departments. Some are from computer science, some from electrical engineering, mechanical, civil, all various types of faculty members are there. And we do work and teach data science and machine learning there to various departments. Now, IITs at least IIT Bombay has a core course in data science. Every department has, right? That is because of this new education policy. It has become part of the curriculum, and we are engaged in that as well. If you want to know more information, this is one easy link here that you can browse. You can search name on internet, and you'll find more research that we are doing. All right. So, as I said, materials is something now I really like, and there are various reasons of liking it. And the way I describe materials is not what we have learned in materials engineering, right, or in metallurgical engineering. The way I see materials is that they are everywhere. We ourselves are made of materials, right? So anything that you see synthetic, right, and it's truth, absolute truth, that we will have to go through it. That sometimes we may be needing some types of implants, right? Replacement of teeth or some implants, synthetic organs, or things like molecular machines which are needed for drug delivery. This is real. This is happening right now. And many of us, if not directly, maybe our family members or somewhere in the society or in extended families are using it, right? So this is how important materials are. You don't, when you say material, you don't have to work just with metals. There are many other types of materials, and they are important, right? So we knew about it, but we should know more about it, because as we are progressing, because of various changes that are happening in the environment around the earth, uh, we are also facing health challenges. Various new diseases are there, right? And as those things are coming, we need more and new materials now. We don't survive with the old ones, right? That's why we need new materials every time. So I would like to acknowledge various funding agencies that have been there to support this research. IIT Bombay, the seed grant, and at various occasions they have supported. MHRD, DSC, BARC, DMRL, through ARDB, ISRO, and there are some private companies, Aditya Birla, universities abroad, CMU. We have Monash University, with which IIT Bombay has a collaborative program. We have shared students, and some recent companies with which we have just started working, Michelin and BASF. BASF is a German chemical company, and Michelin is a rubber company, tire company, right? So they all are now supporting. And I also acknowledge, most importantly, all the postdocs and PhD students, MTech students, and BTech students, those who have been either part of the lab directly or they have taken some research based course under my supervision, without whom this research that you are going to see would have not been possible, right? I'll talk about material design. And when you say material design, it is done based on some data, right? You need to mine that data and you need to grab information out of it. And that is called materials informatics, right? Just chunk of data does not tell you anything. You have to mine and grab what is important. So we need to do some informatics. And once you have discovered the data, you need to now design materials, find new materials. That is called discovery, right? So you have, let's say, a set of data and you have found linkages between various parts of that data set. That gives you knowledge. Based on that knowledge, you do new material development, right? So I'll be using these two terms repeatedly, and I thought this was useful. So keep in mind, and if you have any questions, you can ask me either during the presentation or at the end. It's fine. Now, material behavior, the way we see it, is actually being pushed by various activities and mechanisms that exist at much smaller scale that we don't see, right? Things are happening at atomistic scale, even below scales, like electrons are interacting for various atoms and they make bonds and so on. So it is very important to see how various mechanisms are taking place, interactions are taking place over multiple length and time scales. And thus, this materials informatics or material design is also over multiple scales. You get data not just at the scale that you're observing, not just at the scale that industry is providing. You need to grab data at multiple length scales and try to uh, absorb knowledge at one scale and link it to the other. Right. So overall, the picture looks like this. You may have seen this picture in some textbooks or research papers. On this x-axis, we have length scale. On the y-axis, we have time scale. And if you think about how, let's say, a rocket engine is behaving at high temperature, or how thruster is behaving at very high speed of this rocket, all that is happening because many other small scale and time scale mechanisms are happening, right? And this is a very nice overview of multi-scale modeling. Um, you know, in this large component, if it is made of metals, it is essentially a polycrystal where there are multiple grains. Material science people especially will understand it, that polycrystals, or the metals that we use, are made of small chunks like that, where atoms are mostly stacked in one orientation as compared to the other. And between those two chunks, there are boundaries. There may be various phases also. Between those, there are interfaces, right? So This behavior that we observe here is coming because of behavior of material that is happening within grains, and then the grains are behaving because there are defects. Defects can be the point defects or line defects like dislocation. So if you want to understand how metals are behaving at a given condition, that is happening because the defects are interacting, and that is giving strength and ductility and so on, all the properties. And those defects, if you see at a much lower scale, those are surrounded or are made by atoms, right? A vacancy is a missing atom, and it is surrounded by multiple atoms, matrix atoms, right? And those atoms are together because there are certain bonds between atoms. Those bonds are defined by electron interactions, right? So that is, spatial relation or length relation between atoms to material property. Now, if you think about the interaction, imagine how fast electrons move, and imagine how fast or the frequency at which atoms vibrate, right? That gives you a sense of what is the rate of reaction at various time scales. So, if you just make a small indent or push metal on the surface, that's a very slow rate reaction. You are able to see it with your eyes. That's it's a slow reaction. That's why you are able to see it, right? Our eyes can capture only that kind of time scale. You cannot, even if it was possible to show you electrons literally in front of you, you wouldn't be able to see what type of reactions are happening because those reactions are much faster, right? So we have various time scales of events, and we have various length scales of events. And if you want to design a new material, all these information needs to be understood and captured in form of data. We can capture data about atomic bonds and transfer it to the next length and time scale. We need to capture data about amount of defects and how defects are interacting and take it to the next length and time scale. And we need to understand how grains are interacting and then transfer it to next time and length scale. So we are essentially worried about this data, right? I see. So all this data is not as clean as we see in our AIML course data set. We are given very clean, cured data set, right? When we go through any AIML course. This data has a lot of uncertainty. Why? Because think about again, just atom vibrations. Atom are not at one place. They are vibrating in. You are not able to capture the position of the atom with certainty, right? So there are always uncertainties associated. You can only tell that atom or electron are at a position with some probability, right? So you will see that there is a mean data and there is uncertainty in that data. And with that knowledge, we are recording it. And this data will become useful in overall designing the new properties. When I say new properties, that means I'm designing a new material because I know that that property is coming because of certain type of atoms, right? Another important thing is, which will become more critical, is that how you put those atoms together, how you process your material is again important because the property is not just because of composition. Process is a very, very critical step. Material science people may have learned it already that if you heat a material quickly versus slowly or cool down a material slowly versus quickly, it gives you different phases, different properties, right? So processes plays a very important part. And in industry, processes are not just these single step processes, there are multiple steps processes, right? And again, things are not so clean as we see in textbooks, right? If you have seen shop floor of, for example, large industries like Tata Steel, many things are happening, right? So that's why grabbing data with the awareness of the statistics, how clean the data is very, very important, right? So we can design materials by going forward. So we can start grabbing multiple types of atoms and we can put them together in various configurations and see what is happening at the end, right? That is without target, we are just mixing and matching and calculating all the possible properties. That is called a bottom-up approach, right? But if someone tells you that I need, a thruster of certain high temperature strength that can sustain certain amount of pressure and temperature, that's your target. And if you start from there, And based on whatever information is available to you about existing mechanisms and materials, if you start from there and start developing and try to understand what type of configuration should be there between the atoms, how the material should be processed, and so on, that is called top-down approach. Someone at the top is telling you what needs to be done. So, in both cases, we have some relationship. In the bottom-up approach, we have scientific cause and effect. In the top-down approach, we have engineering relationships of performance and resources. Performance is what the industry or the lab has told you, and the resources are all these. What type of machines you have, what type of processes you can employ, what type of materials as ingredients you can use, because based on the budget, not everything is at your disposal. You're limited, right? So before we jump to this area of machine learning, we used to do a lot of computational methods, computational material science and computational mechanics, right? We did a lot of atomistic simulations to see how a small atomic size crack tip, when um, exposed to a load, how that small crack tip, atomic crack tip will expand, how it will become a large crack, right? Will the material survive or not? Will that crack survive or not? Sometimes, if the cracks are very, very small and loads are small, even small cracks actually can gel together. The material can be recovered, right? We also developed a lot of finite element models and various types of solvers. And our interest that time was to analyze the behavior of existing materials, right? And that's where the story began. That while doing that, we realized that our methods were actually very, very slow. They were taking a lot of resources. So the first part of my presentation is to help you realize that the core computational material science has some components, and the machine learning can actually be used to accelerate that instead of simply using data, right? So here are some examples of what we did earlier, and we still continue to we continue to work on these areas. So we do a lot of in-house code development. For example, how metals deform. So metals deform elastically and plastically, right? Depending upon how much load you're applying. So we have developed, in-house massively parallel codes, and we maintain our own cluster, which has more than 400 cores now. Pretty old, but they do decent job. Where the simulations are run in parallel. Earlier, the simulations used to take up to a month. Now they take a few weeks, right? Sometimes a few days if the simulation is smaller. But this is what is needed. Like if you run a smaller simulation or smaller domain of geometry, that does not give you sufficient information, right? You need to have large chunk of material so that you can understand statistically significant behavior of material. What you see here is a micro pillar of a metal. This is a single crystal. Essentially, there is no grain boundary. If you compress it, there will be deformation. And in metals there are slip planes and directions. And because of those, the plasticity happens along certain planes. It is constrained on those planes, and the shear will happen along some certain directions. Right. So you see these slip steps, right? And it is important to understand that, because as the loading condition changes, as the temperature changes, the amount of slip, direction of slip, and all this will change, and it will overall affect the properties like yield strength or UTS and all, even the fracture, right? Or fatigue. So our models can capture the behavior of single crystals, like you see in this chart. This is aluminum single crystal behavior for various crystallographic orientation. That means the loading axis is along a certain crystallographic axis, right? And we can also simulate things like fatigue. This is an example of titanium 5 aluminum single crystal. This particular alloy does not have vanadium. If you add vanadium, it will become a very well-known Ti6 aluminum 4 vanadium alloy, which is used for aerospace and biomedical, right? This large amount of aluminum also restricts twinning. Otherwise, there is also a lot of twinning, titanium, right? So This is a typical deformed metal microstructure where you see green, multiple grains, and these lines, which are not by mistake or they are not scratch marks actually, they are the strip lines. So this polycrystal has been deformed, and these black lines and these light gray lines are essentially telling you that because of dislocation movement, there has been interplanar displacement, and that is what you see as trace on the surface. Right? We can simulate such polycrystals by creating synthetic microstructures using open source programs or in MATLAB by applying tessellations, or we can just grab the statistics from X-ray diffraction or many other techniques and recreate realistic microstructures and can put them to realistic boundary conditions and can observe which grain is deforming more and so on. Right? Our programs can handle multiple models in a single simulation. I can actually introduce one type of model in one grain, other type of model in the other grain, and so on. I can actually run an atomistic simulation for one grain and a continuum simulation in the other grain. Right? This work has been published recently, 2022, in International Journal of Plasticity. Overall, what you need to simulate such things is you need orientation. Crystallographic orientation means what is the plane normal to each grain, and what is the size of the grain, how many grains are there, right? And all that. What is the composition? And apply realistic boundary condition that you observe in the experiment, and you can analyze it. These are the things that you will not see under optical microscope. Some of the things you will not see even in scanning electron microscope, because scanning microscope shows you only the surface. By using such simulations, you can do cross section and can see what is happening inside the grain, what is giving rise to the deformation that you are seeing on the surface, right? This is an example of a fatigue simulation where the picture that you see on the top left is orientation image of Ti64, which is titanium 6 aluminum 4 vanadium, the alloy about which I was mentioning earlier. And this is the lamellar structure, which is a typical of quickly cooled Ti6 aluminum 4 vanadium. If you cool down it slowly, you will see QX grains, some chunks of beta phase along the grain boundaries, but in this case, it has been cooled quickly, so there are lamellars of alpha and beta. Some of these may actually have even finer structures of alpha beta layers at nanoscale and microscale, right? So this has been scanned in SEM using EBSD method, and then that statistics has been used in Dream3D, or you can use MTEX, which are open source programs, and this synthetic microstructure has been created. And you don't see exactly needle in this because the size of this RV is much smaller than the size that you are seeing here. But the statistics that you see in experiment is completely captured, right? So we are actually numerically talking about similar structures in both cases. So once this structure is ready, we run it through various boundary conditions that replicate cyclic deformation. And along with the just grain morphology, we also now can play with the orientations of these grains. We can assign various types of textures that you see in deformed Ti64 in industry, right? This texture thing is very important because texture represents how statistically grains are oriented in that polycrystal. And that orientation plays a big role on the overall mechanical deformation, right? So the model does a very good job. It can capture the stress-strain cycles that you see in experiment, and we can run it for very large number of cycles. However, now the challenge is that this particular simulation had about 30,000 elements, right? And each simulation used to take about a day, which is a cheap simulation, by the way. A day of a simulation like this is crystal plasticity finite element, is not a big deal. We have run even 6 days, we have run even 30 days. However, it is expensive, right? We are spending energy, spending time, and after 30 days, we come to know that the simulation was not either useful or it did not give the correct result. Although we do testing before running such simulations, but at times it happens that the behavior that you're observing is not what you were expecting. So you need to change something in the material, right? So that is, I re-emphasize that simulations of classical type are expensive, even if you have tremendous amount of hardware power, right? And I'll be repeating it whenever I show you such example that we are spending a lot of energy on running these simulations and we need to think about alternate methods. So rather than running for 50,000 cycles, for example, where you see material failing in the lab, we can run it for only, let's say, 3 cycles, 5 cycles, maybe 10 cycles, right? Because there is a very well established theory that if the material is going to fail at 50,000 cycles, its signature should be seen much earlier. Remember when we started learning about metals, we were given a very simple test how metals harden and fail. There was a very simple experiment given in all the textbooks that you take a wire and you bend the wire up, bend the wire down, and do it multiple times. After some time, the metal will become hardened at the bent location and it will break, right? So think about that material if it is made in form of a, let's say, uh, dog bone shaped specimen and given multiple number of cycles, and let's say it fails, whatever happened to that material must have happened at first cycle as well. Some part of that must have happened at first cycle, right? That is the methodology that we are applying. It's not something new, it has been there in the literature, but we are going a step forward that rather than running just 3 cycles of the simulation, which is able to capture this fatigue interpreter parameter, means a parameter that will be able to tell you how much fatigue will happen or the material will fail or not, right? Uh, Even beyond this FIP, fatigue interpreter parameters, we are applying machine learning also, right? Now, let me restate this that we are actually not running 50,000 cycles. We are running 3, 5, maybe 50 cycles. So that has already reduced the amount of effort that I could have put, right? On top of it, we are calculating these fatigue interpreter parameters, which are functions of how much plasticity has happened in the material, which is given by this delta gamma. It is also capturing on what plane the shear is happening, on what plane the crack will initiate. That is also being captured in this FIP, right? And still the simulations are expensive. And I'll show you that on top of it, how we have make it hybrid by applying machine learning. We are able to do this instantaneously. You show us the structure and we'll be able to tell you how prone to fatigue a particular material is. Work is in right now in review. This is an example again of crystal plasticity simulating residual stress in Ti-6-4, right? So we do not simulate the complete solidification process. We assume that grains have already nucleated and they are in just solid state, and starting from there, they are trying to squeeze, right? And their dimensions are decreasing, and that's why the residual stress is coming. And by doing this high temperature to low temperature transient simulation in crystal plasticity, we are able to estimate where the stresses will be. The part that you see in blue is a melt pool that we don't simulate. We simulate the nearby area which has solidified, and that is going through phase changes and plasticity, high temperature plasticity. Gives pretty good estimates, right? But this is an ongoing work. The student will graduate sometime next year. However, we are very close to what is seen by doing ad hoc simulations in finite element. The part that I love most here, and the part that researchers love most in these kind of simulations, is that at least we are able to incorporate the physics. For example, creep, high temperature plasticity, phase changes, and so on. Contraction, right? Thermal contraction as the metal cools down, right? Now, this plasticity business also does not happen at continuum scale. As you may be aware that it is happening because of line defects, dislocations, or because of grain sliding, or because of, let's say, vacancy movement, high temperature plastic deformation because of creep, right? So to understand that, we have this open source parallel framework, which is called Multi-Scale Dislocation Dynamics Finite Element Program, again developed by one of my students. In fact, one of the first PhD students who graduated now works for Micron. In this, we capture how much slip is happening on every slip system, or total slip which is happening on all the slip systems, by measuring what type of dislocations exist. This is LS is the total dislocation line length on slip system. What is the velocity of those dislocations? What is the geometry of the slip systems on which they are moving? right? And by doing all those calculations, we know what is the rate of plasticity in the single crystal where we have this pool of dislocation, right? And by arranging all this and solving it iteratively, numerically, we are able to do very nice studies. For example, we can study this behavior of deformation of micropillar that I showed you in the beginning, right? Now it is my choice whether I introduce a single dislocation in the pillar or multiple dislocations or multiple pool of dislocations. We can also study things like what is the stress field of dislocations, how the dislocations, if they are on one side of the grain boundary, if you apply a shear stress, whether they interact with the grain boundary and how they pass, what is the stress at the interface and so on, right? In this example, you see there are two dislocations in the beginning and you compress it, the dislocations will start bowing. They'll become more dislocation because they multiply as you deform. And some of the dislocations will escape the surface. And when the dislocations escape the surface, they leave a step. And that's the step that you saw in the first slide. There were multiple steps because of right? So these are the simulated steps that you are seeing here. This is an example of grain boundary and dislocation interaction where the dislocation has come from the left side and it has crossed the grain boundary. And because the dislocation has crossed the grain boundary, there is a small step at the boundary. That is called residual Burgers vector. These are some of the more complicated simulations using the same tool called dislocation dynamics. These are bicrystal pillars. These two single crystals have been joined along the diagonals. They are being compressed, and because the orientations of these two parts are different, you'll see one type of steps on the left side and other types of steps on the right side. Right? Now, bicrystals are important to study because they give you a good sense of how the grain boundaries are contributing to strength overall. Right? So you can study multiple such bicrystals and can design your own polycrystal and even composition. So if there is a grain boundary across which dislocations cannot cross, that is supposed to have higher strength. If the dislocations can cross, that bicrystal will have lowest strength and so on. And that is something that has been observed in microscopes also, and we can simulate it. So these are the simulations that we did. The first one is a rigid grain boundary simulation. That means as soon as the dislocations hit the interface, the velocity will become zero, right? And there are transparent grain boundaries. The dislocations can completely cross the boundary, and there are semi-transparent. That means there are some dislocations already existing at that. These are also very expensive simulations. These used to take about a month, and we applied machine learning to these as well, right? And we are able to now see results again in few seconds. This is all data driven, apart from the physics driven machine learning that I'm going to show you. This is probably the last example of physical simulations. These are some fracture simulations, again, open source development in my group. This is elastodynamics, where we introduce a straight crack and introduce a pulse here, right? Shock pulse, and we are trying to analyze that if the material is gradient vertically or horizontally, or how the crack fragmentation changes because of the pulse, right? If the pulse is stronger, the crack will fragment more. If the pulse is weaker, crack will fragment less. And it talks a lot about how the fracture toughness is changing as a function of pulse. Right? This is a polycrystal fracture simulation. In this case, there is a tensile loading. This is a compressive loading. This is a finite element phase field fracture simulation for hydrogen embrittlement. The hydrogen is being introduced from the surface, and these are the initial cracks. As the hydrogen diffuses to the crack tip, the load is also being applied, and since crack tips are the most potential areas, they are the highest stress concentration areas. Hydrogen actually trinkles to the crack tip first and makes the material brittle, and crack propagates even more. Right? Some more simulations where for the first time we introduced that the fracture toughness, critical fracture toughness is actually not isotropic, it is anisotropic. That means if you deform a polycrystal, the crack always does not propagate in the horizontal direction if you apply mode 1 type of arrangement, right? The crack may go up, down, it may show a very different path. That is happening because crack does not see the fracture toughness of the matrix material as isotropic. Otherwise, the crack always would have propagated horizontally. But in this case, the fracture toughness is anisotropic. That's why wherever there is lowest resistance to crack, it propagates in that direction. This particular simulation took about 30 days, right? And we did multiple of these because we did not get the desired results in one time. And how many of you have gone to a server room, by the way, a computational server room? How many of you have seen a server? Not a desktop, not a workstation, but a really large chunk of computational server. You have seen. How many nodes have you seen? Or what type of tower have you seen? Yes. Yes. Exactly. Yeah, that is what I'm talking about. So where did you see it? Okay. So basically in a cluster room, we have multiple of these racks. If you have a huge facility, you have really large number of racks, and all the racks have your so-called nodes. Now nodes are the actually things like desktops and workstations. They are much larger machines. Every node has maybe 32, sometimes 64. If the nodes are larger, even more number of cores in each of those. And there is a master node, and that master node communicates with all the nodes in the cluster and tells which part of the job it needs to do, right? And these facilities run so much and they do such a large amount of computational stuff that you actually need to cool them down, right? You can imagine that if a simple laptop that you are using can get heated by just running Microsoft Office, you can imagine what type of heat is generated in a multiple node cluster, right? These facilities are actually cooled down drastically using chillers, not ACs. ACs don't work, but we have something called chillers where the cooling is done by using fountains and dropping water. That is another science. So running 30 days of such calculation means you have wasted a lot of resources, and then you have got one result, one picture that represents the experiment, and that motivates why should we find alternate methods, either data driven or hybrid, right? So the question is that physics based simulations are uh, they are good because they are using the theory that we have learned over the years. And theory is sometimes robust, sometimes it is weak. We are using empirical relations. We are at times good only with the data, right? We do not understand the theory, we can just use the data. But the idea is that if we have spent already so much of efforts in establishing physics, and physics is good representative, why should we ignore it? Why should we completely move to data science? Isn't it? Data science is dependent on two things. Number one, how good is the data, and how much data do you have, right? So the idea here is that either data driven or totally machine learning driven methods are probably not going to be useful. We'll need to come to something which is hybrid. And the next examples that you see, they are all machine learning examples that we have done now over the probably 8 years or so, right? So what we need to do is uh, we have some knowledge of current materials, current processes, and performance. Right? Performance does not mean lab test. Performance also means how the component, large scale component that is actually being used at the scale of engineering, how that is performing. Right? We have that type of data. We need to mine through that data, right? And after mining, we'll be able to extract the data which is useful, right? Find correlations, and based on those correlations, you either find a new process or new material, right? And once you have found something satisfactory, you manufacture it based on the process knowledge that you have grabbed, and then do some tests at lab scale and at large scale, right? Some of those tests will fail, right? But during this exercise, you have collected a lot of data again, and that data is more targeted. It's cleaner data than what you had earlier. Now you repeat this cycle multiple times. right? And remember what I showed you in the beginning is that whenever you are collecting data or doing any synthesis or exercise, there is always uncertainty. The material data that you are capturing has uncertainty. Also, the method that you are applying also has uncertainty. Even your computational methods have uncertainty. So at every part of that cycle, you have those uncertainty, and good thing is that you should be aware of it and make sure that they are part of your calculations and the next projections, right? When you do this cycle multiple times, you will at some point you will hit the target, right? Target is the unique solution that you are looking for, and the byproduct, which is again useful for some other exercise, is the data that you have produced in this, right? So this is the main cycle of data driven discovery. And as part of this cycle, you may need data either from lab, or sometimes you may also produce data by doing physical simulations. The kind of simulation that I showed you. For example, if you do not have data of yield strength or UTS or fracture toughness, you may run some simulations either in commercial software or in homegrown softwares or open source softwares, right? So there is a lot of other things are also involved. For example, material and structure design. We are talking about material, we are talking about process design, but then how the structure is designed, that itself plays a big role. And that does not appear in this directly, right? But when you are testing a component at industry level or component level, that structure design is taken apart here, right? So there are many other things that are part of this cycle. So overall, if you have these tools together, that can be something useful for digital manufacturing, right? There is an article that appeared of mine in ET Auto. Here is the link, and you will also find it on my webpage, in which I talked about how computational material design using machine learning can be useful for digital manufacturing, right? When we started in 2019, the first example that we did was how to design a binary alloy, right? Now, this design driven by machine learning has to be targeted. So in this example, we focused on elasticity constants, because before you model plasticity or before you model any other property of a material like metal, the first thing that you need to know is the interaction of atoms. And interaction of atoms is nothing but this is pure elasticity, right? So first thing that you need is what are the coefficients of elasticity, right? So we captured data of various types of metals from open source databases. And we also found a lot of data in papers, which was not reported in the databases. So we had this so-called augmented data set, and it was cured data because we had manually gone through every row and columns of it, right? So there were total about 42 elements in that data set. And based on that data set, we were able to predict some of the very interesting properties. So what we do is shown here. This is the elementary step of any material design, right? So you have a material name X in your database, and you have certain property value. For example, let's talk about titanium 6 aluminum 4 vanadium, right? So you know titanium is part of it, aluminum is there, vanadium is there. You do not know more than that. You may also have some processes associated with it, right? You need to now know what are the properties of titanium and aluminum and vanadium and how much fraction of these elements exist there, right? And based on that, you need to collect some of the intrinsic properties, like how many atoms, how many electrons are there in the outermost shell of titanium? What is the radius of titanium? What is the radius of vanadium? What is the molecular, what is the atomic weight of titanium, and so on? Those become your intrinsic features, right? And you list all those. And out of those intrinsic features, you later figure out that not all are important, only some are important to target the property. Those become your fingerprints, right? So, for example, we are as human identified by our fingerprints because those are unique. One may be having some overlap with some other human, but that's why we do complete biometric. We did do a biometric of eyes, and we do all the fingers, right? So that makes a unique set. And as you do more and more biometric, it becomes less likely that your identity is overlapped with someone else, right? The same exercise we are doing here. We are trying to calculate trying to grab more and more intrinsic properties so that we have more fingerprints. And we are saying that, okay, this material has some set of properties. So P11, P12, P1, first index is the first material, second index is the row in the database, right? So the idea is that every material with having certain fingerprints will have a unique set of properties. So this material to property correlation is one type of problem that I want to solve. So essentially, my machine learning method will give me some function in virtual form, not exactly functional form, not in mathematical form, but in virtual form, that if I input the fingerprint, it will be able to tell me the property, right? Although now there are methods using which you can also come up with functional forms. You can do regression and you can come up with a functional form also in which you introduce intrinsic property and predict the property directly, right? Or the second problem, which is more challenging, is that if someone tells me the property, can I set up inverse problem such that I come to know what is the composition of that material? That is a very challenging problem. That is the problem that most of the industries want to solve because the first problem is open-ended. Take large number of elements and predict any number of properties. Second problem is the top-down approach, where you are doing very targeted exercise that I need a unique property for my thruster. I need to have certain creep strength. I need to have certain melting point and so on. Right? It's a very challenging problem because uh, given the limited data set we have in science and material science, there are various solutions possible unless you put right constraints to it, right? Like boundary conditions. So this is the general overview. And as I said earlier, that there are many challenges. Main challenge in solving that problem is that from where do you get the data, right? So there are databases like we have Materials Project, which is probably one of the earliest databases on which we have compositions and properties of materials, and most of those properties have been calculated using atomistic methods, and that is where the problem is. Atomistic data that you calculate is so clean that there are almost no uncertainties of processes there because it has not been synthesized in lab, it has been just digitally created. So only computational uncertainties are there. So this data is of limited use. It definitely gives you precursors about in which direction we should research to find a new material. However, on top of that, you also need to mix it with either real data or add process knowledge, right? Similarly, we have Materials Cloud, we have Yardbase, we have OQMD, we have Aflow. All these are Alloy databases. Yardbase is a DFT database for electronic materials and so on. They are all open databases, and some part of these databases is also commercial. So some of the cleanest data and exotic data, that means some of the newest material is also commercially available. So if you go to these websites, you will definitely find large chunk of data, but you will realize that the hottest materials which are currently being used, they'll be hidden somewhere and you'll have to pay, right? So as I said here that this is not sufficient. So when we embarked on this problem, we first did binary alloys. We found some data on Materials Project. We did a lot of literature review. It was manual work, by the way. I mean, I really, commend the work that my first MTech student did. He went through a lot of papers and manually collected on Excel sheet, created a very large database of about 2,000 rows. It's a huge data set and about 50 columns. It took him actually two MTech students. First student graduated without doing significant machine learning work, but he was able to create a large database. Plus, he was able to find out methods how to collect database. Second MTech student picked up from there, and he very quickly applied the machine learning with a collaborator, and we learned during that one exercise. And then we said, okay, binary alloy is done, and binary alloy is so simple. Based on that, we also predicted multi-component alloys because see, when you are collecting the data of binary alloys, there are just two elements. But if you mix many binary alloys and do averaging, you get the properties of multi-component alloys also because different binary alloys have different elements. Right, so we started this high entropy alloy work, in which the original data set was available, and it had about 400 rows coming from Oak Ridge National Lab. But that was not sufficient because it was already published. So now, what novel work could you publish? So we again started doing literature review, and this was my first PhD student who worked on machine. So we created a database of about 700 rows, all exotic and new high and this is probably the largest high entropy database we have. We need to check it carefully, but at least when we publish the work, it used to be the largest database. So this is a multi-scale machine learning framework, right? We have various properties in the database. For example, ionic radius of element. We have lattice constant. We have melting point. We have density. We have formation energy of various binary alloys. We have number of valence electrons in the outer shell and so on, right? So this database was added to the existing Oak Ridge database, and we did data mining here. After data mining, we understood some patterns in the data, and then we created features, complicated features. Simplest feature that you can create out of a database is a rule of mixture feature, right? For example, if you have 5 elements and you know the modulus of elasticity for those 5 elements, the modulus of elasticity of the alloy can be represented as the rule of mixture modulus of elasticity. Do a weighted average of the modulus of elasticity of the elements and so on. So by doing various feature engineering, we created alternate features. And then after that, we created stacking fault energy, which is important to initiate plasticity in metals, because stacking fault energy is the one that tells you when the dislocation will nucleate. And dislocations are important for metals. Without that, there will be no plasticity. So we definitely want to understand what is the stacking fault energy. And density is another important property. We do not pay attention to density, saying that it is just has something to do with mass and volume. But density also has a very strong correlation with the modulus of elasticity. Why? Because the denser the material, more closer the atoms, and it will take more energy and force to stretch them. It has correlation with the modulus of elasticity. Right. So these two properties we calculated, and then based on that, we created several independent regressors, and those regressors could predict hardness, which is a very important engineering property, yield strength, peak strength, fracture strength. Right. This was done over multiple length scale, as you can see, because some of the properties are mesoscale and microscale properties, and some of the properties are macroscale properties. Right. So the chart that I showed you in the beginning, which was a multiple time and length scale chart based on physics, we were able to reproduce it partially using machine learning. Right. So overall, we were able to predict some unique high entropy alloys, which are shown on the top left corner. These alloys do not exist right now. And we are not experimentalists, so we are looking for experimental collaborators who in their labs can try some of these compositions, because we do not have just compositions, we also have their process recipes. Right? Now, when I say we have predicted something, that does not mean that you go to the lab and this will be the first attempt of production, right? I was showing you uncertainties with every attempt. There are good chances that we will hit the mark, and there are still, let's say, 90% good chances, but there are 10% bad chances we may not hit the mark. But we are closer to reality now. We don't have to start from scratch. We are already very close to where we should, which elements we should try, with which we have more likelihood, and so on. There is a very well-known HB chart which shows strength to density relation, right? And this chart is used a lot in engineering materials because it tells you that overall where are ceramics versus where are composites, where are metals, and what type of metals have higher strength to density ratio, and so on, right? So the boundary that you see here, this boundary, is the existing HB chart boundary before we started the work, and some of the alloys that we have predicted are actually pushing this boundary. So our alloys have much higher strength as compared to what was already existing there. We were able to also correlate how the yield strength changes as a function of grain size and processing. So for example, if you just arc melt a metal, it is supposed to have much larger grain size. Solidified metal has large grain size. and thus it has also lower hardness and lower yield strength, right? If you deform it, the grain size will reduce. So hot rolled material usually has lower grain size than that. If you roll it further and anneal it, the grain size will reduce and strength will increase. All that we are able to capture as a function of phases. So we are also able to capture that what phase will exist in molten metal versus when you roll it, what phase will be there and so on. So this is a beautiful exercise which at times taught us precise targets. The other times it taught us what workflows should be used for designing new materials. So it was always a win-win situation. These correlations that you see on the bottom left are the same prediction that I showed you on the previous slide, the yield strength versus actual yield strength and so on. Right. This is also a published work in Computational Material Science and Journal of Alloys and Compounds recently. George has also graduated now. He works for a private company into the same area. Right. Now, the data is not always in terms of numbers. Some of the data is in visual form. You take pictures of microstructures, right? Or you take macro pictures, sometimes macro defects, right? And companies are interested, and as researchers, we are always interested that what is the cause of a macro defect in the material, right? Or if I collect a microstructure, what is the strength of it? Can I directly, without taking it to microscope, can I directly tell it? Right. So those type of problems. For example, this is a multi-phase material in which this is all synthetic, by the way, and this was our one of the earliest exercises because we did not have any data. Now, some of the industry partners have come forward and have contributed with similar data. In this case, we have a synthetic structure where we have a low elasticity modulus white phase and high elasticity modulus black phase, and the amount of black is increasing. That means overall this material has overall higher modulus of elasticity if you apply simple rule of mixture, right? So we set up a computer vision problem here by using convolutional neural network, where each of these images are shown to a CNN network, right? And then you do several manipulations by choosing the number of layers, by choosing the type of convolution, by choosing the nonlinear function. We use ReLU here, but you can try many other. Um, and then you try to relate this structure with the property in which, in our case, it was modulus of elasticity, right? Modulus of elasticity, if you just talk about in elastic material, it is nothing but it is the stress at a given strain. If you fix that strain, that is modulus of elasticity, right? If you do not use this nonlinear function, you can never capture nonlinearity, right? This problem is rather very simple because there are only two phases, and we are deforming the material very close to yield point. There is very low amount of nonlinearity which comes because of plasticity, and ReLU was able to capture it. ReLU, you may be aware, ReLU is nothing but it just takes the positive x when you pass it any x, it drops the negative x, right? You should do this exercise, by the way, and I give it to my students also, that if you do not have the nonlinear function, you will be getting a super linear function always. The input will be only linearly correlated to the output. You should do that exercise by yourself, right? All right. So what it shows is that again, you can have a very good correlation between the predicted stress and actual stress. You are able to capture it with very low amount of error. This is the mean of error, only 0.87%. R2 value is 0.992. And this is training and validation, which is obvious because all the data has been seen by the model. And this is the final training, means all the data that was used for training and validation has been shown to the model now. And again, the results are pretty good, right? In this case, we ran some additional simulations, fresh simulations, which were not seen by the model at all. So this data, blue color is the unseen data, this color, right? And the cyan color is the augmented data, means if you have a microstructure, if you flip it by 180 degrees, it is the same microstructure. If you do the tensile test like this or like this, the property will not change. By using those physical rules, we did some of the augmented data generation, and it was able to do pretty nice thing. Just for curiosity, we also used some additional data which was not part of the training. This blue point here is the data point for which there is 0% black in the microstructure. That means all the low stiffness phase is there, low elasticity modulus phase is there. And this blue is the one where everything is black. All is very, very high stiffness, right? Now, machine learning is actually an interpolation methods. You may be knowing that. So, for example, machine learning can do linear regression in a different way. But all it is doing is that if you give it 2 points, it will predict the best. It will give the best result between those 2 points. If you try to predict outside those, it will not be so good. The uncertainties will be very high. The predictions will be haywire completely, right? However, just to do that simple exercise, when we looked at the results for white phase, pure white phase, 0% black, it did a decent job. It predicted that white phase has 70 GPA E, modulus of elasticity, right? Which is a nice surprising outcome because that data was never shown to the model. We started from 5%. So it did a nice extrapolation in that case. The reason was that when you look at 0%, there is no geometric nonlinearity. Those black phases that have been introduced in the microstrip, they have not participated there at all. However, if you look at this part where there is 100% black phase, that the model was not able to extrapolate to. It failed. The prediction is here. Actually, it should have been here, so it is under predicting it. Right? Fairly decent job still. Now, we have done similar computer vision problems using crystal plasticity also, where we have both huge material nonlinearity and also material geometric nonlinearity also. It's a more complicated problem. I'll show you the results soon. Now, this is the structure. And without we explicitly telling the model tells that, okay, these are the regions which are giving higher modulus of elasticity to the structure. It is able to identify those so-called stress hotspots, right? So these are the predictions of the ML model, and these are the real hotspots that the finite element model was telling. So it does a nice job. It is able to understand that which part of the structure is related to what type of property. And that is what we want. We don't want machine learning to be a solely black box type of method. We also wanted to understand what physics is going on in the predictor. Right. I'll take a small break for water here before I move to a totally new topic. All right, so all the methods that I showed you so far, they are data-driven methods, right? And again, I have personally, I should not say started disliking, but the truth is that data is really either not available, or it is dirty, or it is IP data, intellectual property data. And you cannot keep working on synthetic data because there is not much learning there, right? If you want to design new materials or structure in industry backdrop, you have to see that data first, and it is very dirty. I mean, Manmat will tell you, and it's extremely dirty data, right? But that is all you have in reality. Even if you create something using synthetic, transferring it to industry will be very difficult because those uncertainties that are superimposed on real data, they are very complicated. You cannot synthetically create the uncertainties. You can create only the data, right? So what we thought is that, again, why should we use data-driven machine learning? We should come from the other end and try to also stick to our initial goal. Initial goal was that our simulations were very expensive, and we wanted to accelerate those because simulations are good. They are using correct physics. So let us try to accelerate those as well. And once they are faster, we may be able to generate some more data, realistic data, by adding uncertainties. So let us work on those as well. So simulations, if you think about those, think about a finite element simulation in Abacus or ANSYS or any commercial finite element program that way. They are nothing but they are solving systems equations. For example, if you think about elasticity problem or plasticity problem, at the background, you are just solving Ku is equal to F equation. K is the stiffness, U is the displacement, F is the force, load. and that load can be the displacement or the actual load. You're solving this equation, right? Now, boundary conditions will change, your F will change. If material changes, your K will change. That is stiffness, right? And whatever response you get, that is U. If boundary conditions are of temperature type, your U will be of delta T type. If they are of mechanical type, U will be of mechanical type, right? So it is important to solve these PDEs, so-called partial differential equations, where you have uh, two or more independent variables, right? And all the finite element solvers are doing that. Even in fluids, for example, you are actually solving partial differential equation. That is how you represent a system. So this was our first example that we did for solving elasticity in a complicated domain, the domain that I showed you earlier, similar to that. So we have a domain where we have some voids, missing material. We have some fibers. That means in terms of materials or metals, we have intermetallics, for example, right? And when you look at voids, voids as such don't have any interface. They have interface with air, right? But you can just say that those interfaces actually are not interfaces, those are free surfaces. In terms of fibers, we have this interface with the hard particle or a different type of particle or second phase versus matrix. It becomes critical to define the boundary conditions at these interfaces, right? We are applying various types of boundaries. In this case, this is an example of traction here, and domain omega is shown here, and then we may have some displacement boundary condition, right? Our problem was around this momentum balance. So we have this divergence of stress, we have body force, and in equilibrium, all should be zero. That's balance, right? And we may have this displacement boundary condition as shown here. We have traction condition or traction free condition here, and sometimes mixed conditions, right? And then we have our constitutive behavior. In this case, it is elasticity. So Hooke's law, sigma is equal to this elasticity modulus times strain is sufficient. And then we have this small strain formulation, which is gradient of displacement and gradient displacement transpose. This is a small strain formulation. So if you want to solve this using machine learning, we need to come up with some type of optimization method. Machine learning is doing nothing but optimization, but you need to give the functional form to that, what is to be minimized. The loss has to be defined, right? So we defined a loss here. This loss has several parts. Losses says that the governing equation has to be satisfied. The boundary conditions need to be satisfied, both traction and displacement, and also the constitutive behavior should be satisfied, right? So this is one of the earliest methods of so-called physics-informed machine learning, which we replicated for our problem. The method was invented by a US group back in 1890. Even before that, in 90s, some people talked about how to apply neural network for solving physics. We replicated it for solving this so-called composite problem and did a very good job. This is also published now, and we did it in the beginning in collaboration with NVIDIA. And this is now part of their open source program called Modulus, right? So overall, it works like a meshless method. In finite element, we have a definite grid, right? In 2D, let's say we have a rectilinear grid where the whole domain is divided into small squares. We call them elements. In this case, we can just throw random points here. And since there is no mesh, this is also sometimes called a meshless method or collocation method, right? If there are boundaries, we define more points at the boundaries. Like here, we can define less points inside the domain. And you set up your problem and minimize this loss, right? The primary variables, if you are defining a network for stress or displacement, the primary variables travel through the network, and you also define this nonlinear function g. In this case, we used both 10H and ReLU as well, played with it. This is important. These are the results of how finite element works versus how bits work and what is the error between them. So this is a classical finite element result for elasticity problem. We have in this case, square domain. This is, I think, oval, and this is the circular, and this is the square domain. And we have the results predicted by our machine learning solver for PDEs, and this is the difference between them. If you see the error, it is very, very low. It is about 0.36, right? And this method uses a particular type of loss. Now you must realize that if I change the loss, the method will actually become either more efficient or less efficient, because ultimately the ML is just solving that loss. I have to come up with a fancy or more justified loss so that the problem can also run faster. For running these simulations, we had to do about 10,000 training steps. It is very expensive because we were running those training steps on gaming GPUs. We also used NVIDIA's V100 GPUs, which are now kind of obsolete. But it used to take many, many hours. And what we did after that is we have now changed the loss function again. We have more physics involved in the loss function, and method is much faster. I'll show you those results. But this method itself is quite useful because if you change the geometry here, if you change the geometry distribution, you can still do multiple studies. Each of these studies will be very expensive in finite element. If you have to come up with the, let's say if you want to study the stress distribution for a type of composite, every time you have to come up with a new design and run the simulation. If you want to do statistics for that composite, you have to do multiple simulations, right? So every simulation, if take 10 minutes, you'll have to do 10 minutes times those many simulations, wasting energy and time, right? So it's still a quite good method because once the model is trained, you can do all of these in less than a second, every simulation. It captures the effective properties also very nicely. If you have voided increase composites with fibers, if you increase their radius, the effective modulus classes will increase. It captures all that also. And beautiful thing is that if you want to now study material variability or heterogeneity in the material in the domain, such a simulation or such a study in finite element will take a lot of effort because you are proposing that this C, which is modulus of elasticity or elastic stiffness, is varying as a function of x and y. And every time if you have a P changing, that means your material is changing. And if you want to study 10,000 materials, you'll have to do 10,000 simulations. But the way machine learning works is that it reaches the target after doing multiple iterations already, right? So as we are creating these instantiations, it is learning those on the go. And if you look at the comparison here, this is the mean stress across y equal to 0 in the x direction, right? This is the mean stress behavior, and the blue line is the mean plus 1 sigma, and the green line is mean minus 1 sigma. So not just the mean value, but also uncertainty is captured fully. 1000 FE simulations. This is called Monte Carlo because you are randomly changing one of the parameters of the simulation. And to capture statistics, you are doing so many simulations. Every simulation took 10 minutes, 10,000 minutes to do a decent Monte Carlo statistics. 1000 runs, just 1 second in pins. Right? Still a useful one for nice statistics. Right? We have now recently also captured, phase field fracture mechanics using pins. We are able to simulate what is the stress concentration at the tip. We have also coupled it with crack propagation in phase field. So in phase field fracture mechanics, what we do is we solve this modulus of the momentum balance. We solve this phase field equation for crack propagation, right? And then we have this loss function, which is nothing but it is the amount of energy. Sigma times epsilon is the amount of energy that is in the system. As the crack will propagate, it will try to equilibrate the system. So if you minimize this loss, the system is equilibrated and you can feed it to your pins. So this is another thing that is coming up. Right? Speaking of loss, I showed you a very empirical loss earlier. It just had governing equation, it had boundary conditions and so on. Instead of doing that, why don't we just introduce the thermodynamics to loss function? So we can minimize what is the internal work and what is the external work. Internal work is nothing but it is the amount of stress and strain that material is going through. right? You apply load, stress will be generated in the material, and that means there is some internal work there in the material. And external is the one that you have done on the system by pushing the material on the boundaries or by load. So that is the external work. And if the system is in equilibrium, both work should be equal, right? So this is my mu loss function. And by doing that, we were able to actually, the numbers are very small, but I can read you that these are just 1000 iterations of the same physics informed neural network. And by doing only 1000 iterations, we were able to bring the loss to 0.04 times 10 raised to minus 2, 0.0004. Earlier, the loss was 0.36 in 10,000 iterations. That means if you have sophisticated loss function, which is also capturing thermodynamics, you can accelerate your machine learning simulation as well. So this is a very simple domain, and not of much practical purpose. So we played with geometry as well and tried to analyze whether the new method is capturing the stress concentration around these non-homogeneities, and it does a very nice job. If you see, we also now have added plasticity to it. So this is the direct energy method, which uses the loss function that I showed you. And here, this is the machine learning solution, and this is the finite element solution, and it is using all the plasticity that we have. This is finite strain plasticity, not the small strain deformation that I showed you earlier. It has huge nonlinearity and very expensive to run in finite element, right? Again, my small break just for 2 minutes when I go to the last leg of my presentation. And this is something what is going on these days, generative modeling. And everyone is just mad behind it. All right, so this is a good topic, very useful, because the idea here is that why should we always keep training our models, right? Why should we expect our model to reproduce only what we have shown it? It should be reproducing by combining all the signs that it has seen already by itself, right? Going beyond the patterns that we are explicitly showing it. That is what generative modeling is about, and we have applied it to material design. For various examples, I'll show you a few specific ones. This is the first set. On the left side, you see 5 different microstructures of Inconel superalloy, which is a nickel-based superalloy. And it is called superalloy because it has exotic properties at high temperature and high. It shows very high yield stress. It can sustain that extreme environment, and that's why it is used in internals of the jet engines, right? And it is a material of importance because India, I know, is trying to make their own superalloy even now. I'm not aware, I may be wrong, that if we have our traditional superalloy yet, right? Because we buy engines directly, right? The idea is that when we have our own made in India aircraft, everything should be indigenously made, and superalloys is extremely important for that, right? So this is a nice exercise to at least of one use, that if you do not have microstructure data coming from literature, and if you have a very well trained generative model, you can generate reliable microstructures. When I say reliable, they should not be just pictorially pleasant to you. They should also represent, robust statistics. And this was a work done by one of my MTech students who just graduated. And it's funny that he should have joined probably either ISRO or Tata Steel or something like that. The work was relevant to jet engines. He did not go inside, he went outside. He joined Air India. So I wish he could join the companies that make jet engines. He's interested, he'll probably move to the right place. So I see it a useful exercise. You can see that if I train a model where I'm telling that a microstructure has come out of a process, and I train my model by tagging like that class 1 is a process 1, and this is the expected microstructure. Class 2 is another process, and this is the expected microstructure, and so on. If I keep doing that, my model will actually learn that if you want to generate 100 microstructures of a particular length scale coming out of a particular process, it will give me. And we actually applied multiple statistics measures. We did 2-point, we did some of the synthetic image processing based statistics, and the statistics of these generated microstructures is identical to what it is. You will not see any microstructure which is identical individually to any of the used microstructure, which is okay, absolutely fine. But the statistics here is same. These are reliable for us, and we are using it for some of our work. This is based on GAN, and you may have heard something called diffusion modeling, based on which DALE has been developed. We have developed the same model using that as well. However, diffusion modeling is very difficult to train. It uses less data, but difficult to train. All right. The almost second to last example, that in the beginning I showed you that we have this physics-based fatigue model, which has plasticity, elasticity. We can take it through various number of cycles, and it tells in the microstructure which part of the microstructure or grain or phase is more prone to fatigue. Right? Now, I said that still we have to run 3 cycles of simulation, which are still expensive. It takes about a day to run those 3 cycles. We produced about 8,000 such simulations because we needed them anyway. Now, since the data was with us, we used that data for our ML model, and we were able to correlate that if you have a certain type of material which has certain orientation map and morphology, both, not just the shape of the grain. It is not a color game here. We are providing the statistics and we are providing the crystallographic texture to the model, and we are showing it that in which part of the structure there is more chances of fatigue, and that is how model has been trained. This is a forward problem, material to property, and my machine learning model is able to tell that wherever I have this alpha phase, that is more prone to fatigue, and that is what the plasticity model also does. This is the plasticity model prediction. Wherever I have this black phase, which is my alpha phase, there are more chances of fatigue. This FIP map is the one that tells you chances of fatigue. This is FIP, right? And the model is trained using computer vision model. The vision model also tells you that FIP, this black region is the one where the FIPs are in higher concentration. Again, this takes very short amount of time. Now, I don't need to run those 5 cycles of simulation. I show only this part, and I can predict which part of the microstructure is more prone to fatigue, not just the beta phase. Even in alpha phase, if there is heterogeneity and alpha phase is surrounded by multiple beta grains, it will tell you that that is more prone, right? If I tell that I want a material which has least inclination to least chances of failure, what will be the grain size, shape, and orientation of that material? That is a challenging problem, because I can tell the industry partner that, okay, you roll the material in such a way and you heat it in such a way, and you'll get this grain size. And I'm telling you that this grain size has the least propensity to fatigue. And that is what we have done now. We are able to predict. So these are the ground truth microstructures here. And the center ones are actually the predicted microstructures. If you see closely, these are not as sharp as the ground truth, but the orientations in those regions are the same. The shapes of the predicted grains are the same, and the colors, those are the orientations are also the same. And the orientations are also seen in these maps. This is the ground truth, so-called crystallographic texture. This is how we represent them in texture intensity plots. It says that a particular type of orientations are appearing in this particular microstructure. This is the equiaxed basal micro crystallographic texture given to the microstructure. And the other type of texture in this, if you represent it using different poles, it is this. These are the predicted ones. So our predicted model also says that, okay, there are certain fibers which are more in this microstructure, right? Definitely not giving exact replica, but it is able to tell you that if you use a microstructure which is equiaxed, because the shapes have been predicted, and if you use some of these fibers, you will get lowest FIPs. And that is the problem that we started chasing back in 19 when we were beginning to do this work, that thinking that forward work is very, very easy. Reverse work is the actual design work. And that's where we are. The last part of the presentation is this large language models, which I'm sure that any intern of BTech or MTech would like to do these days. Large language models, the first instance of that you have already seen in ChatGPT. Now there is Gemini, right? There are various models available now. And students are using them. They're useful, definitely. In fact, the courses that we teach, we actually allow students to use them. Because ultimately, they are nice tools in a way that, number one, it's difficult to restrict. You cannot ask student not to use them because it's like a Google search now, right? And tool is freely available. Important idea is that do you know how to use it? When Google search had just came, even now, actually many people do not know how to use Google search efficiently, right? There is a way you have to design your prompt, you have to design your text and so on, so that you get the exact answer. ChatGPT has taken you closer to that answer because irrespective of what you type, it will not show you those 10,000 results. It will tell you precisely what you're looking for because it is trained to do that, right? Now, there are many, many, many good applications of that in science also, right? So the way we have used it is that this data problem that we were having, that how to get data, can be solved using this, and that's where we have applied. First of all, there is data scattered in the paper, in the PDF files, in textbooks or in plain text also. The numbers are, as you see in this bottom example, that carbon nanotube, it's a material we have marked it, also exhibit very high electrical conductivity, right? And then, for example, mobility is of something, something number is written. If you want to grab this data, and that is what we were doing for high entropy alloys and binary alloys, you'll have to manually look for it and carefully record the number. And if a number is wrong, your complete model will be wrong. What we have done is we have structured this whole methodology, that how to grab text from PDF and then how to look for keywords using a ChatGPT command prompt. So all we do is we have designed a command prompt and we pass our PDF file to the program that we have created on top of ChatGPT, and it will extract the quantity that we are interested in, and it will extract the number, right? The beautiful thing here is that it will be able to tell you nice correlation, the whole map of the paper and data. For example, this is a chart which we call knowledge graph that has been generated on a PDF file. Ti64 alloy was provided by some vendor, right? It was subsequently polished, and it was polished to certain finish, 0.06 finishes here. And then what was the average grain size of the received material? It was something, something, and then it shows elongation of 15%. It has tensile strength of 920 MPa, and so on. Everything that is written in the paper has now been structured, and we grab it in two forms. Number one, we are interested in these knowledge graphs because they show you nice summary of the paper. Number two, we also grab them in form of formatted tables, the way we want for our other model, the data-driven models. So at least by repeating this exercise to 10 different papers, we were able to grab significant amount of data of Ti64. We use that in some other model. So this data generation and data capture frequency has definitely now increased. It is helpful. We are in a better condition than we were earlier. This work is right now in review in advanced stages. And if you want to read the paper, it is available for free on archives. Like you can search actually just my name and search for automated data discovery. You can grab that paper. A lot of the research that I showed you is either available in articles like EP Auto, or if you search articles of IIT Bombay, some of the articles that I wrote for these free science magazines, online magazines. You can read overall the summary of the research there. We have come up with this tool called padarthproject.org, and it has some of our machine learning models running in the background. binary model alloy is there, binary alloy model is there, and the LLM model is there. What you need to do is you can copy your API, feed it to one of the links that is there, and it you upload your PDF and it will tell you what is the knowledge graph for your paper and so on. Right? Right now, I am paying it actually from my own funds. The idea is to look for sponsors and make it bigger. So all our models are not available, but we are working very hard to make all the work that I have shown you available on this tool so that people can run and see how they work. Even a number of exercises that I have given as part of the course that I teach on materials informatics over the past 4 years, number of tutorials and projects. The idea is to put them on this and so that users can go and run those projects and learn by manipulating the numbers and the modules of the projects, right? With that, I end my presentation. I hope you liked it. If you have any questions, we can have any number of questions because apparently we have a lot of time. Thank you so much for listening. I actually could not believe that it was 2 hours, about 1.5 hours lecture. thanks for thanks for managing to sit there. Any questions? You don't have to be shy about it. So I tell in my all the classes that you should ask questions always. You do not know whether the question is good or bad unless you ask it. So don't be afraid. You can ask me where do you program and so on. Yes. It's a good question. And all the undergraduate students actually, so what I say, don't take it bad. I'm sharing my experience with you. So there are two things that you want to do. Number one is, do you want to pursue this domain as a job seeker? Right? Do you want to see yourself in some ML company? Right? Or do you want to learn it? Okay. Thank you. Oh, acha. Okay. Or do you want to learn it by heart because you are interested? Okay. If you want to get a job in machine learning domain, do whatever you want. Start from finite element, start from data driven machine learning, start from physics informed machine learning, nothing matters. Companies will hire you for another few years, and in future there may be something else, right? So that is the answer to your first question. If you find a good guide who can frame a good problem for you and can direct you to right resources and can teach by yourself by himself little bit, that is fine. If you like the domain, if you like the topic, okay, it depends on which problem you want to solve. It will help you find the answer. For example, are you a person who likes more mathematics, more programming, right? More hands-on by yourself. Then you may be more inclined to do something like solving equations by yourself. If you already know finite element, it will be very easy for you to actually pick up this topic of uh, solving physics informed machine learning. It's a good topic, it's in demand. Very large companies, even Nvidia or Siemens, or you just name the company, they are right now chasing. Okay. You really need to know what you're doing very critically in this. If you are into data driven machine learning, what I have observed is, and even I do that at times, frankly speaking, that you find a problem in that area and there are libraries, and you randomly apply one library or the other and try to find the best answer. And whatever gives you the best answer becomes your final. right? So by that you have, for namesake, some exposure to machine learning. You may not be bound to learn because the library will give you the answer. Best is that when you are using a library, go back and read its theory. Okay. So to shorten my answer now, to summarize, depends on you. How much challenge you want to take and where are you right now. More mathematics means physics informed machine learning, right? More programming and more black boxes means data driven machine learning. Although within data driven also, there are more statistics oriented methods like Bayesian optimization, where you really want to, where you really see how data is behaving, right? So statistics methods are more into that. I can also refer you to some good books that I later found and the books that I now use in my teaching, right? There is a good book you may note down is Introduction to Statistical Learning. It's a very good book. It's a freely available book, and I refer it from first chapter to the last chapter in my course that I teach to undergraduate students. And the book is basically it's a lot of text, and if after every text there is a lab, means exercises, freely available. Anything else? So does that answer your question? You should ask more question and do justice to the talk. You can ask any question.
My question is about machine learning, that on which softwares and what all repositories.
We actually never explored any other language but Python always. Most of the time when we start a problem, we start from Jupyter Notebook because it's a very good tool to line by line check what is happening. When the problem becomes of critical size and we are in production mode, we move it to VS Code. All of these are free, you know. VS Code is something where you don't have to check results in between and you can define that all the results will go in certain and you leave it running. In fact, in VS Code also you can run your notebooks, right? So that is what we do. I never explored R, I never explored anything else. If you ask me more, I find that increasingly using Python, again, I don't want to push back Python and its developers. There is increasingly this understanding that Python is a slow language, very slow language. So if you want to develop something using Python for classical computational methods, not a language of choice. You should develop, for example, your own neural network by using either C++ or Fortran. They are much faster. Fortran and C++ are much faster. We have first-hand experience of it. Yeah, go on.
As a materials engineer, coding is something different. So we are using, I myself have used ChatGPT for this course. So can we be able to do it?
Absolutely fine. So, and I told you that in the course that I teach to undergraduate students, in my exams, I make it absolutely open. There are two parts in the exam. One is a theory exam, two questions. Second exam is a programming part. And I tell them that you can go to any website. The internet is accessible fully. You can use ChatGPT. You cannot use actual chat. Don't chat with your friend, but use ChatGPT. The reason is that ChatGPT, as I told you earlier, it's a tool like Microsoft Office now. You should learn it. It's a good tool, has been trained, make use of it, and it is absolutely fine if you do not know programming in the beginning. And for example, you want to know uh, how to develop a random forest for 10 rows of data and 50 columns of data. You do not know, let's say. You want to start in machine learning. Shoot that question to ChatGPT, let it give you a script and run that script, fine. Who cares? And then learn that program line by line. Definitely do that. When it comes to where the random forest is, read the theory of random forest. You're not doing different than what you were doing earlier. Earlier, you were searching on Google, and Google was leading you to the link of SourceForge and whatnot, right? Or repositories and various Google groups. You were making more effort, right? If you want to do that as well, sometimes you may find actually better answers, but absolutely fine if you're using ChatGPT. Don't be shy. I would by my choice, would like to answer your first question that as materials engineer, you're not a probably a good programmer, or let's say you don't have access, or the courses are not oriented. It's a kind of universal problem, more so in India. And increasingly, the curriculums are being updated. And I personally, because I have seen, I was a metallurgist, I am still part of metallurgist. It is important. Without learning that, integrate mathematics and the programming, you cannot apply your concepts. Learn it. It's harsh. It's very hard. But without that, you will see only part of your knowledge output. Do that. Right? What else? Which model?
So, for example, you use a my model, right? In which there were two components. So, if I am having a thin film, this is a compound of diamond carbon and copper, can it be used for predictions property as well?
So in thin films now, composition is one thing. The structure of thin film is also important. Like if you have second phase particles, let's say diamond are the suspensions, the shape of the diamond and so on, all those become important. You cannot solve this problem just as a tabular data problem. Either you include the statistics of the phases in your tabular data, or you use two problems now. One is the composition problem and the other is the computer vision problem. Then only you can solve it completely. We are right now, the project is actually publicly listed. If you search my name and IITB Monash Academy, we are working with BASF now to design these such nano composites. Right? Similar problem. We are using graphene instead of diamond in polymers. Yes.
Any more questions?
Yeah.
It is possible a student can go over to for 6 months project with IT. If you find that it's better project, then it is possible for them. But at least one or two students.
You mean short-term projects or? So I always take interns. Like during summer, I always take. In fact, I'll be very frank that most of my interns have been actually more productive than our own BTech students because they are engaged in some other domain, definitely. So I find it difficult to grab students for materials because, as I said earlier, that material is just tagged badly. Right. So, lot of interns I have worked from NIT, and they do really, really well. And to the extent of publishing papers. Like back in 17, I had an intern from NIT Jaipur. Very simple paper, nothing about machine learning. But that time I was not doing it. But you were very sincere. We published a paper. Has been cited twice. Fine. I mean, for a BTech, getting a paper even without citation is fine. Yeah, definitely, definitely. We can do that, yes. I have not looked into semiconductors yet, but I am interested. You know, infringing into a new industry is always difficult. So before I contact semiconductor industry by my own, I actually prefer to first do at my end, show them that I can do it. I am interested, as I said, but there is enormous amount of research going on in that area. There is a dedicated semiconductor lab at IIT Bombay. There is a large group of faculty members from IIT, from electrical engineering and physics department. They have created a center which is very active actually in semiconductor, not just design but also manufacturing. I think there are all type of people. It's a multidisciplinary center, and you should contact definitely. If you search semiconductor manufacturing IIT Bombay, it will lead you to the right link. If you are not able to, you can contact me. I can direct you. Okay. All right. Thank you so much.
Thank you so much, sir, for a very informative lecture. I would now request Muhammad sir to present